Okay, this will be about the shadow problem. So we have Jim, who is 6 feet tall, walking away from a lamppost. Here is my lamppost that's 15 feet tall. And Jim, who is 6 feet tall. And he's walking away, so he's going to the right in this case, from the way I've drawn it, at 4 feet per second. What is the rate of change of the length of Jim's shadow? So his shadow, because the lamppost is shining from this direction, his shadow would end up being to the right of him when he is 8 feet from the base of the lamppost. So you do notice that there are two triangles formed, the big outer triangle and the small inner triangle. Now I don't put the 8 on this triangle on purpose. When you are working with rate of change and you are doing these differentiations with respect to time, you must label the sides that are changing with a variable. Even though at this moment in time, when Jim is exactly 8 feet away, it's currently 8, that can change. So this needs a variable, the distance from Jim to the lamppost. I'm going to put it as x instead of 8. The shadow will also change depending on where he's at. The further he goes, the smaller the shadow will get. So both of those need variables, and you do have similar triangles. You have the big outer triangle, the small inner one. The big outer one, the entire bottom would be both added together. X plus y would be the entire bottom of that triangle. So we can set up a proportion now. We can use this proportion to solve for y if necessary. But we can also differentiate first and see if we ever need to plug in y. So we can set up our proportion. We have, and you may have started setting it up differently if you've already tried this problem. It doesn't matter how you start it as long as you keep things corresponding. So from the big triangle, I'm going to take the left side, 15, and the bottom side, x plus y. From the smaller triangle, now I have to go in the same order. Left side, which is 6, to bottom side, which is y. Before I differentiate, it's a good idea to cross-multiply, because we don't like differentiating or pretty much doing anything when we have fractions, if we can help it. So 15 times y is 15y. 6 times x plus y is 6x plus 6y. And you might as well get like terms combined before you differentiate. So I'm going to minus 6y from both sides. Gives me 9y. Now I'm ready to differentiate. So when you're differentiating with respect to another variable, differentiating y with respect to t for time and x with respect to t, you take the derivative. Normally, derivative, if I just said derivative of y with respect to y, it'd be 1. So technically the derivative is 1, but then you also have to include the differentiation piece. You have to say, well, I took the derivative of y with respect to time, so I need dy dt. So most of the time we don't even write the 1 in, we just say 9 dy dt. Same thing happens with the x. Technically the derivative is 1, but you also need that differentiation piece of dx dt. So I did not need y or x even. They didn't need to tell us x was 8. What I do need is this 4 feet per second. Since we labeled this from the lamppost to the person as x, 4 feet per second would be dx dt. It's the velocity, the rate of change with respect to time for that snapshot. So 4 feet per second, we're going to plug that in for dx dt. So 9 dy dt equals 6 times 4. And now we just solve for dy dt. 9 dy dt equals 24. Divide both sides by 9. dy dt equals, and if we reduce that fraction, we would get 8 over 3. Dividing both of those by 3 would let us reduce that fraction. If it asks for the answer as a decimal, you could also put it as 2.6, repeating. Still feet per second. It's going to be in the same units as what they originally gave you, and they told you 4 was in foot or feet per second. So that concludes how to do the shadow problem.